Hello, our presentation is called The Experimental Investigation of Custom Composite Rocket Body Tubes. My name is Emma Dorsey.
And I am Annette Shizuso.
As an introduction, rockets must be strong enough to withstand the launch process, yet must also be lightweight. Rocket bodies manufactured of a composite material, such as fiberglass or carbon filament, are both strong and light. To be manufactured, resin-coated composite filament is wound around a cylindrical core called a mandrel at predetermined overlapping wind angles. Once the resin is cured, the mandrel is removed, leaving a composite tube with a higher tensile strength than stainless steel. The objective of this project is to identify the most efficient wind angle that produce cured tubes with the highest strength to weight. Additionally, an objective is to modify the filament winding machine to achieve the desired weight and volume matrix of fiberglass. Finally, to successfully perform destructive and non-destructive tests designed specifically for this project.
The methodology for this project is to test 3 tubes that were wound on the X-winder, each consisting of 10 layers. The 3 tubes vary with helical wind angle, the first tube having 16.41 degrees, the second 17.44 degrees, and the third 14.78 degrees. The 10 layers consist of 2 hoop, then alternating helical hoop 3 times, and then ending in 3 hoop layers. A 2-to-1 thin epoxy is used with the fiberglass strands, and the composite is then wound on a cardboard mandrel and cures for 24 hours. After curing, the tube is sanded smooth before testing. The desired weight ratio for fiberglass to resin is 3-to-1 and the corresponding volume matrix is 60%. The initial results showed that the average volume matrix was 59.66% with an average weight ratio of 2.24 to 1. The weight ratio was lower than the ideal 3-to-1, meaning that in winding the tubes there was excess resin. Figure 2 shows the 3 test tubes after fully cured, and Table 2 shows the matrix volume ratio and weight ratio results, and showing that there was a low percent error of 0.56% for the matrix volume ratio and a 25.32% for the weight ratio.
In future work, the next step is to perform a failure analysis on the constructed tubes. Next, destructive testing will begin. The 2 tests that will be performed are the hydrostatic test and the compression test. The hydrostatic test is a way to test the strength of certain vessels such as body tubes. The tube will be filled with an incompressible fluid and then will be pressurized to test the strength of material. Figure 3 shows the CAD of the hydrostatic testing rig. For the compression test, it will measure the tensile strength, the ultimate strength, the maximum elongation, and breaking strength. This will subject a sample of the material to be tested by a controlled compression load until failure occurs. For non-destructive testing, the 2 tests will be the strain gauge test and the beam bending test. The strain gauge test will determine the strain of the material. The strain gauge will either be glued on or embedded into the body tube while it is winding. The beam bending test will measure deflection and bending stress. A sample from the tube will be tested by loading the free end with a set amount of weight and measuring the deflection with the ruler. Finally, we are going to compare our custom tube strength values to the company manufactured tubes values.
And we'd like to give a special thanks to our professors and technical advisor, Dr. Patrick Browning, Dr. Gregory Thompson, and Dr. Joseph Pasolka. And a special thanks to our sponsors, West Virginia Space Grant Consortium and the WVU Experimental Rocketry Club. Thank you for your contributions.